Hey class, I hope you're ready for the next stages of exam two. So I thought we would take a look at, we can look at the three remaining problems. So yes, on Tuesday we covered Kruskal and Prem. So we'll look at tree traversal today, both breadth first and depth first. And then we'll finish with Dijkstra. And that should take up most of class. And if not, then it's an early day. But I think, honestly, I think we're going to have to rush a bit to make sure it's not a long day. So let's start with problem 2.2 of the trees. So we're given a graph, simply connected graph. And we're asked to begin at node F and perform a breadth first traversal of all of the other nodes in reverse lexicographic order. And so if you remember, lexicographic it is the method that we use for sorting items in the dictionary, so alphabetical ordering. You test the first letter, and then you test the second letter, and you test the third letter. But it's also a more generic criterion in that you test criterion 1 for some ordering property, and then you test criterion 2, and so forth. So it's really just a series of tiebreakers. So you begin over here, and then if it's a tie, then you deal with this, and then if it's a tie, you deal with this, and so forth. So that's lexicographic. But whenever we use it in the context of letters, we're talking about alphabetical order, and so reverse lexicographic is the other direction. So we're traversing, so we can only branch out from F wherever there's an edge. So F is connected to D, B, E, and C. And so if we were to sort them and then go sort them in descending order, so from last to first, then we would go E, D, C, B. And so at this point we've already visited 5 nodes. So and we know the answer. We begin with F, we visit these in reverse order, and then there's only one node left to visit. So that one is not as bad as it sounds. You just have to become comfortable working with the terminology. Okay, so now let's jump into the other two, which we get to code for. Okay. So now we want to iterate through a tree, and so whenever I think of a tree, I always think of an HTML document. So let's code up an HTML document that has this form, and then let's take a look at both what we're asking for and then what it is to use pre-order, in-order, or post-order traversal. Okay, so we need to declare our document type, first line, and then if we follow the structure, we add an HTML node at the root, and then it had 2 children, a head and a body. So head, and body. And then head had 2 children. It had a meta tag, and these can be used to give various hints to the browser. But the most common declaration that you'll see using a meta tag is a declaration of the character set, the character encoding. And so what tends to be taught in terms of character encodings is the Ascii character system, because we use the Latin character set, and all of the English letters that we use are encoded in Ascii, in just those first 128 bytes, I guess, or those first 128 code points. Sorry. And so values 128 through 255 are kind of left open. And so, there are various approaches for how you get characters like the tilde or that French C with the squiggle at the bottom. Eventually I will remember what that squiggle is called. So those are all encoded in the Latin 1 character set, which is still just 1 byte per character. But then it doesn't encode any of the Eastern languages. So one approach is to use 2 bytes for every character, so that you have 65,000 distinct characters that you can represent instead of just 256. Another approach is to always use 4 characters. But the approach that I favor and that the web tends to favor is UTF-8, where you just use that most significant bit in a byte to say, okay, if it's 0, then it's an ASCII character. Just treat it like an ASCII character. But if it's a 1, then treat it as a character that requires 2 bytes to represent, and then you can use various other hints to scale all the way up to 4 bytes. So I think UTF-8 is the most clever solution, and then it's also compatible with people that assume that they're working with ASCII. So if you have to choose, if it's your choice, pick this one, unless you know a specific reason not to. Okay, so the other child of head was title. So if you want to put something up here in the title bar, then you'll want to declare the title within the head of your HTML document. And so this is exam 2, problem 2.1. Okay, and then we have the body, and the body has a div and a script. Okay. And so this will really be the root div that you can act on. And there's a few ways to interact with the HTML document whenever you're writing with JavaScript. So right now, we're just going to interact with it by reading it, by traversing it. But the responsiveness that users look for whenever they're interacting with a web page really comes from very complex JavaScript application with several files, and typically it all gets compiled down into just a single file. But all of the tags and all of the HTML elements that are included in the page, or a good deal of them, are all handled by JavaScript. They're created and they're merged into the tree, and then they're pulled out whenever their life is expired. And it all begins with this root element. Right? So whenever you work with one of those complex JavaScript applications, you'll have a root element like this. But there are other ways to interact with it. So if you just have a simple page, and really all it is a form, and you either aren't familiar with the modern method of creating a single page application, or you just think that it's overkill for whatever it is that you have to do, then there are these custom attributes, these data attributes that you can use, and you can access, you can use these HTML elements to store data just like you would the instance of a class in Java or C# or C++ or a struct in C. It could just be used for data storage. And I'll note it briefly just so that you're aware of it, but that's really just for for your own interest. It's not a part of the what we're covering for the exam. So this would be your entry point. And then we were supposed to have a script tag. And it's not always necessary now to declare the type, but it's still, I think it's considered good form. Okay. So I told you that there would be a callback, and the first thing I'm going to do is change what I had on the exam, where I used the arbitrary node.value. If we create it as an actual HTML document, then we have to use node.tagName. So that callback that I showed you becomes this. Okay. And then we also need a recursive function in order to traverse the tree. And so these, with depth-first traversal, it's a little bit like being lost in a maze, or the way I think of it. And you know, if you're lost in a maze, so this might not work in a cavern or something that has a potential isolated point, like a pole or something, right? But if you're lost in a hedge maze or something, a topiary, I think they're called, then you can just put your right hand on one wall, and if you keep walking, you will eventually exhaust the possibilities of the maze, and you'll find your way out just by holding one hand against the wall. That's a little bit what we do whenever we're traversing the tree, especially depth first. We keep our right hand on the wall, and we keep walking until eventually we've visited every node that there is. Okay. So we have to take the order type, because I'm going to show you both pre-order, in-order, and post-order, and what the difference is between the three. So the order type, the current node, and then the callback function. Okay, so if it's pre-order, then we invoke the callback function before we visit any of the children. Okay, so that's pre-order. And then children is, it's essentially an array. I think it's an HTML collection, which is derived from an array or has some array-like properties. But it provides a length property. So we're iterating over the collection of children. Now, we test for the chance that we asked for in order. And in my opinion, in order traversal only makes sense if you're dealing with a binary tree. But here we'll say if one child has already been visited, then we visit the current node before we visit any other children, which is completely compatible with the case whenever we're dealing with the binary tree with in-order traversal, where you visit it between the two children. Okay. And then if this is to be a recursive function, at some point we have to call the function itself. So and this is the recursive part. The order type, we visit the same in the same order at every level. It's always pre-order, it's always in order, or it's always post-order. So we just forward that whenever we call it recursively. And then we visit the children at index I. So we're looping over all of the children. We've given them a serial number, and now we visit them in order of their serial number. And then we forward the callback function as well. And then post order is visited after we visit all of the children. So you can see where each one would be invoked, depending on how what method of visiting order you're applying. Okay, so now I believe the question asked for pre-order, but if I give that to you, then you don't have to actually code this out to get the answer. So we're going to visit it post-order, and then I'll leave it to you to do the other. And here we need some way to get this root node, and so we can get elements by we can get it by ID, such as here if it's provided. We can get it by class name if we've defined CSS classes. We can look it up by class name and it'll get the collection of that. But you'll see that here we're getting just a unique element, get element by ID. And here we're getting a collection, get elements. So the only one that allows us to uniquely grab a node is if we retrieve it by ID. So that's the preferred method for grabbing a specific node. But in order to take advantage of that, you have to define the ID. And so we've only done that for one node. So as it stands, we would have to get the element collection by tag name. And so we look for HTML, and then we pull the very first result. And then we forward it the callback method. All right, so let's copy the path, and then let's open it in our browser. If we inspect, we get the view of the HTML document here, the document tree, and here we see that our post order traversal visited them in this order. Everything appears to be working. But now I want to show you just one modification on that, and then I'll leave the rest to you. So it is possible to define an ID for the HTML root node. Okay. So we could have used get element by ID, where we don't have to put this index accessor at the end. If only we had given it an ID to begin with. Right? So if you know you're going to need to grab something later, then you should give it an ID so you can grab that very specific element, and then you don't have to handle all of these one-off conditions. Okay. I'd mentioned the data description. So how do we do anything with that? Okay. So the Mozilla Developer Network, MDN, data set. The documentation is pretty good, or it's excellent, I should say. And so if you're lost with HTML, then you can come here and it'll help you out. So here we were using get element by ID, but it's possible to make a query against it in the same way that CSS applies styles, and you specify some combination of tag name and CSS class. That's an attribute for it, and then you can test lots of other stuff. You can use these virtual selectors to apply certain styles to the fifth child and so forth. So that is exposed. Everything that you can do with CSS to grab a collection of elements is exposed. But we want to, if we wanted to store data in an HTML node at that level if we wanted to start appending data on it. Then we could do so by prefixing it with data hyphen, and then everything that's available there is available in element.dataset. So if we grab that root node, so we'll call it root, then in dataset we have description provided to us, and we can log that. And if you remember, we had provided that over here. So you can grab these values and you can store them if you want to manipulate the document using just raw JavaScript. And I encourage you, while you're learning, just to understand sort of the options that are available as you build out web pages, because at some point in your career you're likely to touch them. Then this is one approach if you, for whatever reason, tend to not favor the single page application approach. Okay, so now we've done this. Let's take a look at Dijkstra. Okay, so Dijkstra deals with finding the shortest path in a graph, and we're going to do this one using Node, which is still JavaScript, but now we're using it to build desktop applications. Oh, change the name. Excellent. So you see, if you can't get to Hello World, then you're in trouble, right? So quickly fixed, right? It wasn't too terrible. Okay, so now we can at least do that much. So let's move this to the bottom, and it'll just tell us that everything ran. I don't like to leave the program empty because I always wonder whether or not it executed, even if I know it probably did. So I always like some reminder whenever I run it. Okay, so we need to declare a vertex. And in JavaScript, functions are first-class objects. So it's not a weird thing to use it as a variable, right? But also, we can use it. We can store property data on it, just like an instance of a class. So just to show you that this is something that's possible, let's follow through with it. So this is similar to how we would declare a class in Java. So we would give it private variable names, and they would be accessible as like this dot underscore name and this dot underscore edges, and the type would be inferred from this. But in JavaScript, you have to really work to get private variables. You have to use certain techniques called closures in order to get them, and it can be done. And if we have time to go over the module pattern, then we'll do that. But when declared in this manner, the properties live with the object. So whenever you do new vertex, you'll get a name and edges, but they'll be publicly accessible. So like I said, you have to really work for private variables. So appreciate what you have when you're working in those other languages. Okay. So then if we want other stuff to be included whenever we call new vertex, then we have to define it as part of a prototype, or that's one approach for adding it. So we say, okay, whenever we do new vertex, I don't just want these properties, I want this function called addEdge to be included as well. And so we push it on to the end of our edges collection, whenever we call addEdge. Okay. And then it's always good to have a toString method. Even in JavaScript, I'll still insist that we should apply that. So I like interpolated strings because it makes it obvious how it all should fit together. You see the placeholders, and it just has always felt cleaner to me. So we can still access this edges property that's declared on the this object whenever you have an instance of a vertex. Right? So that's accessible over here in these other functions that are defined on the prototype. And so even a function that was added later to the instance of vertex but not to the prototype, so you can sort of glue on functions after the fact in JavaScript. Like in these other languages where they're compiled, you can do inheritance and stuff like that, but whatever the function or whatever the class was whenever it was instantiated is essentially always the class, unless you get really into the weeds with some like compiler manipulation stuff. So those types are always, or those instances are always basically the same. But in JavaScript, once you have an instance, it's essentially a clone, but that clone goes on to live its own life, so it can accumulate other functions and properties after it's been instantiated. And so only the prototypes are guaranteed to be present down the line for the edges. And then in this case, because vertex is this function, these properties can be assumed to exist. Just like they can accumulate properties and functions as well, instances can lose them if someone goes out of their way to delete it. But that's that's not really worth discussing at this moment, because while you want to protect yourself from making errors or from being inundated with properties that are really internal to a class, it's one reason to hide them, is just their need is entirely contained within the instance of the class. And then to expose it everywhere that has visibility of that instance is to, it's like having a really long menu at a restaurant. Sometimes it's nice to just go somewhere where there's only a few things that are really good, and then you don't have to look at the menu too long. Right? So that's one advantage of private variables and private functions in classes, but we don't have that available without closure here. Oh, and then whenever I do an assignment, I always like to end it with a semicolon. It's not strictly necessary in JavaScript, but I'm particular, so I insist on that. Okay, so now we have a vertex object, and we need a graph. In Java, in C#, we would define an edge because that's an instance of a thing. But it's not clear whether or not we need that. So here, let's fill this out, and we can go back and we can comment it out later if we don't need it. But for now, I think edges can be maintained in just a key value dictionary. But had we included the edge class, it would have looked like this. Because I believe some of these class definitions were provided in the notes. So if you were to map it directly from the notes, you would end up with an edge class or something that should be newable. And then the only other thing we can think of at the moment is that it needs a toString. Okay. And then again, I tend to favor interpolated strings. So lead with the name, and then other information that you'll want if you're debugging. Again, it's worth putting in the effort in advance, because if you've ever been frustrated while programming that you just can't see what's going on, then you should appreciate the value of helping yourself out down the line by providing yourself as much meaningful data in some compact and readable way as possible. Like it's really yourself that you're helping out with these functions, these toStrings. Okay. But we don't properly need the edge class right now. So. We can delete it later if it never finds its way into life. Okay, so now the prototypes for the graph function, or the graph class, if you want to think of it as a class, because we'll certainly use it that way. Okay, and so this is how we get a new instance of something, and so it looks just like a class. Now we get to decide, there is a class keyword in JavaScript, but I think it's more confusing to use that. I think it makes more sense to use functions and prototypes in JavaScript. But if you end up using React or I believe Angular as well, probably Vue.js as well, then you'll end up using class instances. But if you're developing with raw JavaScript, which again, I encourage you while you're learning to go through the pains of that, to just gain experience and understand how everything is working, because as you get later on in your career, you're sort of relying on the work that you did earlier, and that you can understand it. And then whenever you get asked really challenging problems about how to make something faster or lighter weight, you can make these informed decisions. So it sometimes takes a while for the payoff, but it does come down the line, and it begins with the work that you put in now to understand sort of what's going on here. But if we wanted to treat this like a class, and we insist on capital letters or whatever for our class names, then we can develop that convention. And if you have an opinion on it, if you think it should be new and then a word with a capital letter, then that's great. Opinions are great. I always really enjoy opinionated programmers, because it means that they do it often enough to feel very strongly about it. But we're not going to do that right now. So if you want to in your code, it's up to you. But if it looks weird to have new and then something that's all lowercase, just let it look weird for a little bit. Okay. So we can add a vertex. Now we need to be able to add an edge. And if you recall from our work with spanning trees, adding an edge is the same as connecting vertices. So let's connect the vertices. And we do that with a source ID, a destination ID, and then the weight of the edge. and then same as last time, we want to be able to look it up in the forward direction or the reverse direction. That is source to destination or destination to source, because it's an undirected graph. Oh, I'm sorry. Really, all of this, I had intended to increase the zoom on this. Oh well. Sorry, you'll have to squint. Not exactly sure how to zoom in on this right now. Okay. We're in connect vertices. Right. So the forward ID. So we're building up an ID here for looking it up. And it's going to be readable because we're debugging. You can always shorten it later, but if you make it too machine friendly early on and not human friendly enough, then it becomes really difficult to debug. Okay. So now the edge, we don't actually need a class. The edge is really just kind of a placeholder, essentially. So we had the class up here, and we could use that. We could do new edge and uncomment this and get it. But I want to show you your options. Okay, so here, if you really like dealing with classes and stuff like that, then you can do this, and it's just like programming with classes in Java and C# and C++, where everything is public. Okay, and these are your class variables. They're publicly declared, and these are your functions. Okay, and we can do that. You can see it works just as expected. But in JavaScript, there's another way. So instead of defining it as a class, we can just use the JavaScript object notation to declare a new JavaScript object. So this is really simple syntax. It's just the curly braces. And it gives us a collection of key value pairs. And some of the values can be functions. So you can have you can reference edge.toString, which we will do. This is another way to declare an object in JavaScript. It's probably the more efficient and the more common way. But unlike with these, if you're programming against an interpreter and you make a change to the function, if you do it on the prototype, then that change is made everywhere. All of the existing instances get the new function. But if you do it in this fashion, then only instances created after the change was made would get those modifications. But that's very it's a bit of splitting hairs at this point. Right now I just want you to become familiar with what is possible whenever creating this. So let's finish typing this out and I'll explain what it all means. So we want the edge's name, and then to us the edge will always be the source, destination, and weight triple. So that's what we would like to report in our toString. Okay, so I've used a lot of the ECMA script 2016 or 2015 or ES6 syntax, where I declare functions as like lambda functions. So func is input parameter, and it's an arrow function, and then we have the method body here, and it returns some value, right? Or it doesn't return, it's just an action. So I tend to favor this just because it's really brief. It uses fewer characters and draws less attention away from the body of the function. So I like it because it's cleaner. But if you want to use this, right, this keyword inside of a function for an object that's created using the JavaScript object notation, then you have to declare it as a function. You can't use that ECMA script. Otherwise, you have to do call or apply or something. You have to invoke it in such a way that you pass the object that should be referred to using this into the function. And so it's one of those JavaScript quirks that you have to look out for. But if you just want to know something that works, right, just tell me what works and I'll do that, then do it like this. So the methods that you declare, right, so it needs a function name, so that's the key, right, for this object. And then the value is declared as function, and then the rest of the signature fine. And you don't want to name these functions, right? Because the name is actually accessed this way. So if you don't want to create some weird cases, then do it this way without a method name. So the value is this function, and then you can access these properties that are declared on the object. So name is now visible within this function, right? This dot name. Source is visible. And then this right here is another feature, I believe, that was added with ES6. So one of the updates to modern JavaScript. If you have a variable and you want the name of the property on your object to be the same as the name of the variable, so that when you access it, it's accessed as edge.source or edge.dest. So basically, if you want to copy the variable name as well as the variable's value, then you don't need to do source where this is the key and this is the value. JavaScript is now smart enough to know, the JavaScript engines are smart enough to know that this is going to be the key, and then the value is borrowed from whatever the value of that variable is at the moment that this is created. Okay, so this is another way to create objects in JavaScript. So this is like using classes, this method, and then this is the more pure JavaScript way to do it. Okay. So so we've created an instance of an edge. Now we want to add it to the graphs collection of printable edges. We'll probably want to add it to the edges collection as well. And then we'll want to make both the source and the destination aware of this new edge. So printable edges was a dictionary, key value pairs. So the key is going to be the forward name of the edge, and then we'll track inside edges. So this is just a single collection, but then both the forward and the reverse will be stored in edges. So we add our edge to that first collection. And then we add both the forward and the reverse to edges. And so the distinction is that whenever we're writing it out to the console, whenever we're printing the edges, we want a distinct collection, but whenever we're performing lookups, we don't want to care which one is the source and which one's the destination. It's undirected. It's not supposed to matter. But the workaround to that is to include both and then have both of them return the same edge. So now the source becomes aware of the edge, and then the destination becomes aware of the edge. And so our get edge function will take advantage of the fact that you can look it up in either direction, but we have to recreate the string. So we'll just copy that, and that'll be our key. So if it's found, then we return that, otherwise we'll return null. So rather than have it be undefined, we'll choose to define it as null. And then if we didn't want to maintain separate printable edges and edges collections, right, if we didn't want to distinguish between those two, then the work of duplicating forward and reverse would fall here. And so we would say, okay, well, if you find it in the forward direction, use this. Otherwise, use the reverse key. Otherwise, it's null. So there's multiple correct ways to do this. We're just making a choice. Okay, so now we get to implement our function. So far, all of the work we've done has been to just represent the problem in code. And now we can finally discuss actually solving it. So we're going to give ourselves a lookup table. And then this .vertices is going to refer to the instance of the vertices dictionary on graph. And then whenever you do, for variable in this in a dictionary, the output of this is an iterator over the keys of that object. So we're going to get all of the keys for the has own property satisfying values on vertices. And so distance lookup, we're ensuring that we have an original vertex and we have a terminal vertex, and we're going to visit the nodes beginning with the original vertex, and then we're going to branch out to everything that it can see, sort of like whenever we were growing the blob. Can't remember if that was Prim or Kruskal off the top of my head, but whenever we were growing the blob out by just considering the edges that are adjacent to the blob at that point. And so as we grow it, we'll encounter new paths, and we may have to update the shortest path from well, let's say that originally we're starting at node A and we want to end at node Z, and there's a few ways to get there, such as A, B, E, A, D, E, so forth. And so originally the shortest path to E went through B, and then we visit D, and we find out that now the shortest path to E runs through D. So we need a way to track those updates whenever we find some new shortest path to some node that we're already aware of. Okay. And so those lookups will come from here. And so another way to think about it is, well, we're trying to find the shortest path from A to Z. But if you have some initial vertex, then you can look anywhere on your graph and say every other node, and I guess even the original node, will have some shortest path that's available to you, and you just have to find out what it is. And so with Dijkstra, we essentially maintain this table that finds that entire collection of shortest paths everywhere, if it's allowed to run long enough, and so that we get the full listing of how far it is to every other node via any collection of paths. And so that's what we're trying to maintain. And so one part of that is the distance traveled, and the other part of it is the path itself. So whenever you find some newest, shortest path, then you're not just tracking the new distance, you're tracking the path. Like what highways do I have to take to acquire this new shortest path? Okay, so so those two parts again are path and distance, and we say that the terminal vertex, as we're building up this entire collection of what if I wanted to visit, any other node, what does that distance look like? It starts off infinitely far away. So JavaScript does provide an infinity. Obviously it is not infinite, but it satisfies certain requirements of infinity, such as any number plus infinity is going to be infinity, any number times infinity other than 0 is going to be infinity, and it's going to be infinity is greater than anything that would be stored in the 64-bit number instance. So it satisfies some of those requirements. So we'll start it off there. Okay. So the only one whose shortest path we're aware of to start with is going to be the original vertex. So we could have just updated dot path, and so the other way we could have done this is to say that dot path contains just this array. Distance is 0, because we had initialized in object up here inside of the loop. We'd given everything some object definition, but we're not worried about memory necessarily at this point, or various other optimizations or considerations. Right now, we don't so much care. It's a small problem. We don't really care if we create another object or what the cost is down the line. But these are the types of things that you have to be able to consider sort of what's already there, and like, is there anywhere else that you can sort of speed things up or make it cheaper in terms of memory or processing or whatever. So it's nice to have an understanding of the various ways that you can perform the same action. But here, this is the most readable. We want to remember that it's an object with these properties and exactly what it was initialized to. So we won't worry about updating those previous ones until later on. Okay, so Dijkstra's algorithm maintains a solved set. So once it's your turn in line to sort of grow the tree, then or grow the blob, then you get added to the solved set. So everything initially is unsolved, and then one by one they get moved into the solved set. And once everything is in there, then we know the shortest path from Dallas to everywhere else in America, or from point A to every other letter in the alphabet. Okay. So now we need a method to iterate. How do we know where we go next? See, I've switched to the other style for declaring functions because it's not strictly required of me. I'm not defining it as a prototype, and I'm not defining it as an instance function. So I don't intend to use the this property, so I use the what I feel is the cleaner syntax. Okay. So we have a next vertex. And then we maintain a minimal length, which in order to test that, we start off at infinity and then we work our way down. And then again, we want to iterate over the collection of vertices. But the context of this hasn't been changed to this function, and that was by design. So this still refers to the graph instance. Right? We're defining it. So this is a class function essentially because it's a prototype on graph. So this refers to the instance of graph here. And I purposely did not change it to a function here so that I wouldn't confuse myself. Right? I would have clear line of sight to this variable. Okay. So we're iterating over the vertices. We say if the vertex that we're considering, that's neighboring, or if the next vertex that we're considering is already in the solved set, then just ignore it for now. Continue the loop. Otherwise, if it's not solved, then check the distance lookup, and let's compare the distances. Is the one in the lookup the known shortest path? Is it infinite? Basically, have we not discovered this vertex before? And if that's the case, if it's still infinite, then continue the loop. Skip that one as well. But if it is known, then let's see if we found a better way. Okay. So we're always looking for the nearest neighbor. We're growing our blob, right? And so we're taking advantage of the distance lookup to define whichever one's shorter. We iterate all of the vertices, and then it's just like finding the minimum value in a set in an array of integers. We just continue to make comparisons over the entire collection, and if we find one that's shorter than the shortest one that we already knew about, then that becomes the new shortest one. So that becomes the nearest neighbor. And so that's the point of get vertex. And then for debugging, we want to include the results of this, so that we understand how it is that we're iterating. Actually, I think we want the object, vertex object. So that's done slightly differently, rather than, well, no, let's use that. So vertex does define a toString, I believe. Let's confirm. It does, so we can use that. And then we want to return that result. So now we need to consume it, and essentially we ask that we just solve everything. So while not solved, I told you if we let it run on for the entire collection, then we would get our distance lookup to contain a map of all of the shortest distances from your original vertex to every other vertex in the graph. But to speed the algorithm up, we don't build the entire list. We don't consider every edge or every road in America. We stop as soon as we solve for the terminal vertex. As soon as we move that into the solved set, then we don't have to do any work. So that becomes our new halting criteria for our loop. So we always start with a current vertex, which is provided to us by the get next vertex, which is the function that decides how we grow our blob, how we identify where the nearest neighbor is. And then we want to check, is current vertex null? And if so, break. So if we don't have an accessible nearest neighbor and we haven't solved, then we short circuit here. This is our test that on the chance that we're provided with a graph, the definition of a graph that is not connected. So it may be that our vertex is unreachable. So we test for that. Okay. So now we consider the solve set. Say, okay, if we're working on this vertex, then it is solved. So we move it into that set. We remove it from unsolved, and you remove from a JavaScript object by deleting. So we delete the item with the key equal to current vertex's name. Now we provide ourselves with some debug statements. I always like to leave white space to make it easier for myself to read. It can get a little out of control. Okay, so now, because I'm printing objects rather than strings, in this case I'm printing, I think, arrays. Nope, they're dictionaries. I want the console to print as much of this as it can. It's not worth, to me, it's not worth the time of going through and looping over all of the values or everything. I want a synopsis of what's there. So it's good enough for quick debugging, but if I need more information, I can always come back later and modify these log statements. But I just want a summary of what have we solved and what have we not, and make sure that that both of them are being updated appropriately as we move items over. And then because it's a loop, I provide these empty lines so that I can separate it. It just becomes a little too much to look at if it's all clumped together. So again, we're iterating over the collection of keys in a dictionary. Right? For let key in unsolved iterates over the collection, where unsolved is the dictionary and key becomes the name of the key. So we retrieve the edge. Which connects the current vertex to one of the unsolved vertices. So we look for those edges, if possible, if they exist. So if it does exist, if there is an edge connecting those two, which is what we're testing for here, right? This is shorthand for if edge is not equal to null and edge is not equal to undefined. Right? So we can shorten that in JavaScript to just if edge. Right? And then the context of being in an if statement shortens the test for all of those other conditions. It also tests to make sure that it's not equal to 0 and not equal to the empty string and a few others, I think. Okay. So we use that shorthand. But now we check the lookup table to see if the new distance is going to be less than whatever's already in the lookup table. So we do that by comparing how long it took to get to the current vertex. So the lookup of the current vertex, and take its distance, and then we add the weight of the new edge. We say, okay, if we did this route, is it going to be shorter than the distance that we already know about? So have we discovered a new shorter path to get from A to Z? And we make that comparison right here. And if that's the case, if it's some new, better, shorter path, then we log the path and update the lookup. So again, distance lookup. It's keyed by vertex name because we already know what the original vertex is. So we say for these terminal points, these are the known paths with the known shortest distances and their associated paths. And so if the route running through the current vertex that we are attempting to solve is shorter than the known path, then we take the path that brought us to the current vertex, the path to get to the current vertex from where is it? From the original vertex, from the origin to the current vertex. We copy the path, that's what this is inside of the array. We take a copy of that collection, and then we add the current vertex, right? And this is the vertex instance, not its name, right? It's the actual vertex that we get by referencing this. So that gives us our path. This array defines the new path to that neighboring node. make it aware of this new distance. And the new distance was the path to get here, and then plus the path from here to the neighboring. Okay, and once we finally get out of the loop, we return this, the pair of distance and path from the lookup for that terminal vertex. Okay, so the other thing we're going to need, right, since we have a graph, we need to be able to print it out. It seems a little more involved than a toString, so I call it print. And also, toString returns a string, and print is going to write to the console rather than return a string. It's the different name. So before, we were using this syntax to iterate over the keys of a dictionary or a JavaScript object. Here, you can use object.values or object.keys to iterate over the values or the keys, depending on which ones you want, for a JavaScript object or a dictionary, whatever you want to call it, or hash table or lookup. Okay, so now this dot vertices again refers to the collection of vertices that's maintained as a property or a variable of the graph object, the graph instance. So it's that same collection that we were looking at whenever we were solving it. Now we iterate over that, and we just print out all of the vertices using their toString methods. And then a graph is both vertices and edges. So we want to print out the edges as well. And so we yank out the values collection from the list of printable edges, or the dictionary of printable edges, key value pairs. Okay. So now the function's done its job, doesn't need to return anything. If we run it, we'll either run into issues or get completed. Okay, great. So now we need to define a graph, and then we need to invoke Dijkstra to solve it. So let's see. Yeah. Okay, so we're going to apply this to the graph. I believe that's provided in the book. And then I'll leave it to you as an exercise if you want to use this to solve the one that's included in the exam. And then obviously if you want the extra credit, you would have to either recreate this essentially under your own direction, or you can translate it from JavaScript from the example provided into C# or Java. So again, these with the prototypes and stuff, these are class definitions. So if you were to create it as a class, you would create the graph class. In this case, you would create an edges class in C# or Java, and the vertex class and then you would have the private variables. You would define getters and setters, and then you would have function names that are equivalent to all of these prototype functions. Right? These would be the member functions, the class methods. Okay. And then somewhere in your main method, you would instantiate a new graph. You would give it a name. I like to keep myself updated on where my code is in case I've written an infinite loop somewhere. So we begin by defining the collection of vertices, and then the collection of edges is created by connecting vertices. Okay, so now we create the edges. Connects to B with a weighted edge of 5. B connects to C with a weighted edge of 10. C connects to D. And again, this example is pulled from the book, not the exam. Whenever you do this on the exam, these are your vertex names, and then this is how you create the edges. Right? So C connects to D, cost of 15. D to E, cost of 20, E to A, cost of 25, and A to C, cost of 1. Okay, so we have a graph instance. It's nice to verify that it's doing the same thing that we think, so let's print it out. And then if that works, then we'll invoke Dijkstra. Okay. So we have our vertices, and it tells us the degree of each vertex. We have our collection of edges here and what they're connecting. Right? So let's see if Dijkstra gives us results. So let the shortest path from A to D be given by invoking solve Dijkstra on our graph instance. And then the method, it doesn't take names like we were using whenever we were looking it up in JavaScript or in Java. Here we're actually using the nodes, the vertices themselves, the instance of the vertex class, and passing that around rather than the name and having the graph look it up. So if you, if you're confused by the distinction, then that's one possible bug point where you've confused the identifier with the instance of the object itself. Just another thing to look out for as you code. Okay. So if once you've done all that work, it's as simple as that. You call it and then you print out the results. Oh no, I can't read toString on null. Dijkstra looks like line 92, maybe character 52 instead of get next vertex. Next vertex, okay. Okay, so this one and actually pulled in because I thought it might be simpler to invoke toString. But now it'll just print null if it's null. Okay. Okay, so now if we go through the solve function, we can look for our log statements to find out when we get logs. So each time we call get next vertex each time we enter a loop. Right? So whenever we see get next vertex, it means that we're on another instance of the loop. So we have to find when we invoked the function. So here we're creating the vertices, here we're creating the edges, and then we print out our representation of the graph, and then we begin our loop, get next vertex. The vertex it identified was A. While we were attempting to solve from A to D. Right? So we would expect to begin with A. So let's go back up to the definition. So the very first thing we do is we call get next vertex, and we find what are the neighbors of A. What can it reach that is less than infinitely far away? And then we find the nearest one. So whatever that shortest one is, that becomes the nearest neighbor. It gets moved into the solved set, and we work that one next. So initially we have vertex A that's solved, and then B, C, D, and E are all unsolved. And then we call get next vertex, and it turns out that the nearest neighbor was C, which, if you recall, the distance from A to C was 1. Right? It was the lightest weighted edge in the entire graph. So that moves to the solved set, and then we now consider the edges of both A and the edges of C to find the nearest neighbor, I believe. Let's see. So we get the next vertex. Now we're looking at C. And then it becomes solved. We declare it as being a solved vertex. And we look from C, and then we see what is cheaply accessible, what is closer than whatever was infinitely far away. Right? And we do those lookups. And these just get updated. We update all of these weights, all of the known distances. And then get next vertex, it gets whatever vertex is nearest the solution family, right? So our blob is growing out, and it creates all of these solved vertices, this ever-expanding collection of solved vertices. And then get next vertex kind of subtly does this trick where it looks at that collection of solved vertices, and then it says whatever node is closest to one of those known outposts, and then that one becomes solved. It joins the collection of solved sets, and then eventually it expands, and then whenever it finally includes the terminal vertex, it halts and returns that as the solution. Right, so that happens at the very end. We get our shortest path, and it begins with A, and it goes A, C, D, and it has a total distance of 16. Okay, okay. So you should have everything that you need in order to complete the exam. I hope you have a great weekend, and yeah, have a great time, and I will talk to you all on Tuesday.